Previously on the head of a pen.
Extra dimensions that are large is crucial to producing black holes at the LHC.
Any tiny black hole like that would decay very rapidly.
Suppose you had a quantum fluctuation that occurs close to the horizon, close to the edge of a black hole. So that space itself changes into a positron and an electron. It's possible for the positron to go down into the black hole and the electron to escape. That's called the evaporation of a black hole. All right? And the smaller the black hole, the easier it is for that process to occur. It's thought that at the birth of the universe there were all kinds of different sizes of black holes. And the smaller ones evaporated away.
What they were worried about at Santa Barbara and so forth is the idea that a black hole could be created and then just wander off somewhere else. Now, if a black hole is stable and it encounters other matter, either other particles from the beam, which seems pretty unlikely, or more likely particles in the detector itself, or if the thing goes off into the Earth, matter inside the Earth, it could eat that matter and accumulate it and grow in size rather than decay, evaporate away. Well, that would be a bad thing if, if such a black hole were slowed down enough to, let's say, go into orbit inside the Earth. That's an odd concept, right? But that's exactly what would happen. A black hole experiences gravitation just the way every other object does. And depending on what its velocity was when it was created in one of these LHC experiments, it could just sit there and orbit the Earth, gradually lose energy, eat more and more particles, and then eventually eat the Earth out from the inside. And obviously that could have dire consequences for everything on our planet.
Black hole, for the purpose of the LHC or the LHC concern, is a particle whose gravity is so strong that even light cannot escape from it. And therefore it looks black because light cannot be emitted from it and come to our eyes. So now, this was the classical picture of a black hole until Hawking came around in 1974, and he pointed out that a black hole actually can, because of quantum mechanics, emit some light through the process that's called Hawking evaporation. So a black hole is not completely black, it can emit some light due to this quantum mechanical process. Now, at the LHC, in certain theories, in theories with large extra dimensions that I alluded to before, can be produced and can be produced at a significant rate.
And this is not an exotic physics. It's based on pretty good general relativity. Now, if you make a black hole that's really just one constituent of a proton and another constituent of a proton, that's an incredibly tiny black hole, all right? And its evaporation rate is going to be phenomenal.
The classic theory of Hawking predicts that even though they are produced, they live for such a short amount of time that they instantly evaporate before they have any time to do anything significant. In fact, they don't even have time to move from one atom to the next. That's how they decay far more rapidly, far too rapidly to really be able to move any significant distance. So, according to the standard theory that most people agree with, a black hole lives for such a small amount of time that it can't do anything. Now, so the so-called, that's the very first grounds on which I have no concerns about LHC.
The idea that it could hang together long enough to start attracting in other matter around it is just philosophically absurd. All right. So anybody who says that we could have a catastrophe at the LHC because we can make black holes there, they're missing a major point. They're missing a point that it's really only the very large black holes that you have to worry about sucking matter in. The very small ones, including the jillions of them that were probably created at the birth of the Big Bang, were all evaporated away, so we don't have to worry about them nowadays. And that's what I think, if this theory is right, if this if this theory of large extra dimensions is right, and gravity is strong at these scales, and they do make black holes, I think there's absolutely no worry that they're going to suck matter in.
Okay, so let's suppose that there are extra dimensions that would allow us to create microscopic black holes in LHC collisions. That would be fantastic, by the way. It would be a really fun discovery. We would only discover it, however, if we could see them decay rapidly to lots of particles come spraying out in all directions.
You can think further. You can start then questioning, saying, well, maybe Hawking is not right, and maybe there are special black holes that don't evaporate, at least don't evaporate rapidly, and maybe they have time to move from one particle to the next, and maybe in the process of moving from one particle to the next, because of their strong gravity, they start swallowing one particle, one atom, then another atom, then another atom, and if they do this enough, you can start worrying, gee, they're starting to swallow a number, perhaps a large number of atoms along the way. Could that get out of hand?
Well, first of all, it would have to be that Stephen Hawking was wrong. And Stephen Hawking's work is based on fairly vanilla assumptions about how quantum mechanics works. There's no real reason to believe that work is incorrect. But you never know, right? Science makes new discoveries all the time.
Yes, even if you want to be agnostic and question Hawking's evaporation, the process of production of black holes has been happening all around us, all around the universe, all around the Earth, quite frequently through cosmic rays. So the energies that the Large Hadron Collider will explore are already being explored in the universe all the time by very energetic cosmic rays colliding with other particles in the universe. For example, energetic cosmic rays have been impinging upon the Earth for billions of years. They've been colliding with particles in the atmosphere of the Earth at energies exceeding the LHC energies, yet no black hole has ever been produced throughout these billion years that caused any harmful effect. And the same has been happening not just on the Earth, but in all planets, around neutron stars, around stars, continuously everywhere in the universe, and it hasn't caused the destruction of the universe. So this is an empirical reason to argue that there is no dangerous processes that happen at high energies, at the LHC energies, that would cause the creation of a destructive black hole. And that is probably the most comforting argument, that we don't have to worry.
There are these high energy cosmic rays bombarding our atmosphere all the time, and they have such high energy. It's way higher energy than the collisions that we are going to create in the LHC. Furthermore, this process is going on everywhere else in our galaxy. Every star, every planet in the galaxy is also being bombarded by these cosmic rays, which, if they make black holes when you have a collision like this, certainly should have happened already. People say that, in fact, if you think of all the particle collisions that will happen in the LHC during its maybe 20-year lifetime. Our galaxy has already conducted 10 to the 31 of those LHC experiments already, and it's 10 to the 13th of them are happening every second. And we don't see giant explosions happening in the galaxy that often. We do see supernova. That's like 1 or 2 per century, not, all the time, which is what it would certainly have to be if we're creating those.
So the energies of cosmic rays that come from somewhere in the universe, relative to the energies of the protons at the LHC, are much, much higher. So cosmic rays have vastly higher energies than the LHC energies. They collide with atmospheric particles, which are practically at rest. So they have little energy compared to the LHC energy, but the combination is enough to produce black holes if they were there. If they were there, it would be enough to produce black holes. If the LHC can produce black holes, then cosmic ray collisions can produce black holes easily. And the fact that such collisions have been happening throughout the universe for the whole history of the universe, yet they haven't destroyed the Earth or any other planet or any, is a direct indication that we don't have to worry about.
These particles can have phenomenally high energies, much, much higher energy than the particles that we send whizzing around the LHC by many orders of magnitude. And so when these particles hit the gas nuclei, the nuclei of gas atoms in our atmosphere, they create huge showers of particles which eventually make it down to Earth. And this is happening all the time. In fact, if you hold out your hand, there's 1 cosmic ray muon per minute per square centimeter going through every portion of your hand all the time. If you could see these cosmic rays, they're just raining down in this room right now. They're everywhere.
So in order to draw the analogy between the LHC, where both 2 very energetic particles are colliding with each other, and the collisions of cosmic rays with the atmosphere, where a very energetic cosmic ray collides with a particle essentially at rest, an atmospheric particle, you have to be very careful. You have to compute the total amount of available energy in the so-called center of mass frame. And when I tell you that there is a direct analogy between LHC collisions and atmospheric collisions with cosmic rays, I already take that into account. I go to the center of mass frame where you can compare apples with apples, and that is where the center of mass energies, that is the amount of energy that's available to create black holes, in collisions of energetic cosmic rays with atmospheric particles can be far greater, 10 times greater than LHC energies. So, and even there, even in spite of that, there hasn't happened any catastrophic event involving black holes to destroy the Earth or any other part of our universe.